Good morning, dear students. Welcome to another session of microwave and antenna. So in the previous session, we started a discussion with respect to microwave network theory and passive devices. So in which we discussed all these concepts, that is what is meant by microwave network, how it is formed, what is meant by a junction, what are the ports, and at low frequency, what are the parameters we have to look in for, and at high frequency, what are the issues. These are the aspects what we had observed. Then we had discussed regarding the say low frequency parameter analysis, that is the Z, Y, H and ABCD parameters, considering say a two-port network over here. And we had observed how we obtain these parameters at low frequency, that is with the help of the open circuit and short circuit. So, and we discussed what actually happens at high frequency, that is the microwave frequency range. What happens? How is the physical length compared with the wavelength? So, and what are the why these parameters are difficult to measure? That is Z, Y, H, and ABCD parameters. So these were the discussions. And what is the other parameter we have to look in for when we are dealing with these microwave networks? So that and we discussed one of the properties which is relevant to the reciprocal networks, in which we consider the properties of Z and Y matrices. So wherein for reciprocal network, if we just observe Z and Y matrices are symmetrical, and the parameters are basically characterized by the parameters which are M and E, the electrical parameters. And we obtained this with the help of Lorentz reciprocity theorem. So that is what we had considered. So this is the aspect what we had discussed in the previous session. So in this session, we'll start a discussion with respect to scattering or the S-matrix representation for the multiport network. So in the previous session, we had discussed regarding these representations, in which we had observed that the S-matrix representations for the multiport network. So in high frequency networks or the multiport, say microwave frequency networks, right? What happens is we come across two parameters. That is, one is called as the incident wave and the other one is called as the reflected wave. So for the analysis, right? So this is one parameter which we have to consider in the S matrix representation. So now here what happens is because of the incident and the reflected waves, we need to go ahead with the matrix which is termed as the scattering matrix. Apart from this, these are the conditions what we have to look out. This is the purpose why we have to look in for the S parameters. So here we need to consider the amplitudes which are associated with the incident and the reflected waves which are present at the ports which are available in the microwave networks. So that is what we have to look out for. And when we are doing the analysis, right, we look into another aspect, that is we consider or we normalize the amplitudes, that is these wave amplitudes which are associated with the incident and the reflected waves. We normalize those values in such a way that when we take the square of those parameters, when we take the square of the incident and the reflected wave amplitudes, right, we get the average power. We get the average power. So if I consider the input power at the nth port, so if I represent it with PIN, so N is identifying the nth port. So PII is identifying the input at that port. So it is equal to half of the magnitude square of the incident wave amplitude. So here A identifies the incident wave amplitude, B identifies the reflected wave amplitude, and the suffix what we are using, say N, identifies at which port it is being considered. So that is what it specifies. So these are the aspects what we have to look out for when we are dealing with the scattering matrix. So here we can observe few parameters. So if I'm considering, say, a two-port network, so in this, I'll be having two parameters. One is the incident wave and one is the reflected wave. So here, say since two ports are there, this is one first port and this is the second port. So if I just observe the suffix what is given over here, it tells me that these are the parameters which are associated at port 1. It is associated at port 1. So A1 is the incident wave amplitude at port 1 and B1 is the reflected wave amplitude at port 1. Similarly, I have A2 which is the incident wave amplitude and B2 which is the reflected wave amplitude at port 2. So the same this representation what is there that has been displayed over here. So this is what we have to what we are considering in this case, that is how we represent the S matrix for any multiport network. So now in general, first we are considering a two-port network and we'll observe how these parameters will be related in order to represent the S matrix. And then in general, we'll be applying it for the multiport network. So now here another aspect to look out is this parameter. So that is what is A1 given by. So that is if I observe here also it is the same this thing. A1 is associated with incident parameter. It is associated with incident parameter. So here if I just observe if V1 is the voltage at this point and V2 is the voltage at this point, this V1 and V2 again will be divided into two parameters, that is one is incident and the reflected voltages. One is the incident and the reflected voltages. So therefore, if I just consider, if by definition what we have, A1 is actually associated with the incident wave amplitude at port 1. So if I associate this, this has to be related to the incident parameter of the voltage which is available at port 1. And if I consider that Z0 is the intrinsic impedance of the network which is available, then how do I represent it? I represent A1 as incident wave amplitude divided by square root of Z0, divided by square root of Z0. Now, if I just observe this, if I have to represent this in terms of reflected parameters, in that case, what I have V1 minus V1 plus is equal to V minus of V1 minus. So therefore, I can represent A1 even in this form. That is V1 minus of V1 minus divided by square root of Z0. Now, similarly, if I consider B1, so B1 in this case is associated with the reflected wave amplitude at port 1. So this has to be associated with what? It has to be associated with the reflected voltage at port 1. So that is V1 minus. So therefore we can have V1 is equal to V1 minus divided by square root of Z0. And if I substitute V1 minus based on this equation, I'll be getting this parameter, which is V1 minus V1 plus. That is, this is the incident wave divided by square root of Z0. So similarly, we can have the identification or the representation for B1, A1 and A2 and B2. So therefore, A2 is again it is associated with what? It is associated with port 2. The voltage at this point is V2. I'll be having two parameters, V2 plus, that is the incident parameter, and V2 minus, which is the reflected parameter. And A2 is the incident wave amplitude at port 2. So therefore we have V2 plus divided by square root of Z0, and B2 is associated with the reflected wave at incident reflected wave amplitude at port 2. So therefore it has to be associated with the reflected voltage. So therefore B2 will be identified by V2 minus divided by square root of Z naught. So this is in terms of the voltages, what we are representing the incident and the reflected wave amplitudes. Now, if I consider the current, right, the current is associated in this form. That is, current at this point is equal to incident current minus the reflected current, and I2 is incident current at port 2 minus incident current at, reflected current at port 2. Now this we had observed even in the previous sessions in which we had discussed regarding transmission lines. So there we had come across these parameters also. So it is in association with all those aspects. So this two port network, when I represent, this is how it is actually represented. This is the actual representation of the two port network. This is just a simplified version. So now here, if I just observe what we have is, if I represent the S-matrix, if I have to represent this network with scattering matrix. So there is this one I want to represent with the scattering matrix. So how we have the Z matrix and Y matrix and the H and ABCD matrices, right? In the similar way, we can even obtain S matrix in which we obtain the association of the reflected wave amplitudes with respect to the incident wave amplitudes. So these two are associated with the help of the S matrices or the scattering parameters. So here, how do we go ahead? We can observe the equation which is that is in the matrix form, which is present over here. What we have here, we have the reflected wave amplitudes. So these reflected wave amplitudes is equal to the matrix which is associated with the scattering parameters, and these are the incident wave amplitudes. So if I have to write this in simple form, so we write matrix which is associated with B, matrix which represents the scattering parameters multiplied with matrix which represents the incident wave amplitudes. So this is how it is represented. And since we are considering just two port over here, what we have is we have only two parameters, B1 and B2. That is only two reflected parameters at port 1. One parameter is there and port 2 other parameter is there. So similarly, incident and reflected are available at port 1 and port 2. So because of this one, what happens is we will be having four scattering parameters which make up the S matrix. So this is how the S matrix representation is done for a two-port network. So that is what we have represented over here. So this one we require for identifying few of the losses which are actually present in this two-port network. So this we'll discuss after we finish off our discussion with respect to these S parameters. So now here you can observe that for a two-port network, I am having S11, S12, S21 and S22. So there are four parameters which are associated with the scattering parameter. That is the microwave network, two-port microwave network. So here what we have is now again, if I represent this in equation form, this is how it is represented. So we have B1, you multiply and equate each of the terms. So B1 is equal to S11 into A1 plus S12 into A2, and B2 is equal to S21 into A1 plus S22 into A2. Now, in a previous case, say Z or Y parameters, so where we had discussed. So here, say if I consider this, what we have V1 is equal to I1 into Z11 plus I2 into Z12. Now, if I had to identify one of the parameters in this case, what I had done, I would make say current I2 0. And if I make current I2 0, indirectly what I am doing, I am open circuiting the network at port 2. I am open circuiting the network at port 2. And in that case, I'll be able to obtain what is Z11 parameter, which is V1 by A1. So almost similar concept, but here what we do is we cannot go for short circuit or the open circuit analysis. So as we had discussed, what is the problem? So if we go for that, if we have any active devices, they become unstable, and obtaining short circuit and open circuit analysis in the microwave or the high frequency is very difficult. So therefore, what we do is we use the concept of matched termination. That is, say if I want to measure, say S11. So here you can see that A2 has to be 0. A2 has to be 0. So when A2 is 0, what is this specifying is that port 2 is matched terminated. So what is meant by matched terminated? We are assuming that we put forth a load at port 2 which matches with the characteristic impedance. So that is what we are looking forward for. So we are trying to have a matched termination at the port which is at which we have to look out for. So here, say for example, if I just consider this parameter and I want to measure what is S11. So in this case, what I have to do, I have to make A2 equal to 0. So when A2 is equal to 0, what this equation turns out to be, it turns out to be B1 is equal to S11 into A1. So therefore S11 will be equal to B1 divided by A1. So this is reflected parameter divided by the incident parameter. So that is, and in these two cases, what we have it at both at port 1. But under what condition? Under the condition that A2 is 0. So what is this specifying? This is specifying that the port 2 is terminated with the matched load. So that is what the specification implies. So now here, if you just observe the next parameter, say I want to estimate S12. So if I have to estimate S12, then what I do is I make A1 equal to 0. So in that case, what happens? B1 is equal to S12 into A2. So therefore S12 is equal to what? B1 divided by A2. So if I just consider over here, it is S12 is equal to B1 divided by A2. What is B1? It is the reflected wave, say a reflected wave amplitude at port 1 divided by the incident wave amplitude at port 2 under the condition that A1 is 0. What does this imply? This implies that port 1 is terminated with the matched load. This implies that port 1 is terminated with the matched load. So that is what we are looking out over here. Now, similarly, we obtain the other parameters. So here we have S22, which is reflected divided by the incident parameter at port 2 under the condition A1 is 0, and S21 is B2 divided by A1 under the condition A2 is 0. So that is what we have is we make another observation over here. What are these parameters actually providing? So S11 and S22. These are actually giving you the information pertaining to the reflection coefficient at what? At port 1. At port 1. So if you just observe, this is the port what we are considering. So here we have incident A1 and the reflected B1. They are available at port 1. So if I'm taking this ratio, it gives me the information pertaining to the reflection coefficient which is available at port 1. Similarly, if I take B2 by A2, which is S22, which is associated at port 2 over here, it gives me the reflection coefficient at port 2. So these are associated with the reflection coefficient parameters. Now, what does these two provide? So here, if you just observe S12 and S21. So this is associated with port 1 parameter and this one is associated with port 2 parameter. And in S21, if you just see, it is B2 which is associated with port 2 and A1 which is associated at port 1. So here, if I just make an observation, say if I consider this, A2 is incident wave amplitude at port 2, and you're trying to see what is the reflected parameter at port 1, reflected wave amplitude at port 1. Similarly, S21 also you are doing the same way. You are observing what is the input at port 1, that is the incident wave amplitude at port 1, and what is the reflected wave amplitude at port 2. So you have given the input and you are observing what is the result. So it is like in that way. So you're observing these parameters. So this is what this actually gives you the information pertaining to the attenuation of the wave which is traveling through the microwave network. So in this case, what it is specifying, it is giving you the information pertaining to the attenuation of the wave which is traveling from port 2 to port 1. So here, because input is at, you are associating the input wave amplitude at port 2, and you're observing the output, that is a reflected wave parameter at port 1. So this is what you are looking at, and this is what you are observing. So if I consider that parameter, what I am having is, when you give the input, that is the wave which is traveling from port 2 to port 1. So it is giving you the attenuation of the wave which is traveling from port 2 to port 1, but under the condition that port 1 is terminated. Port 1 is terminated. So similarly, S21, we have B2 divided by A1. So here, what you're doing, you are observing the attenuation when the wave is traveling from port 1 to port 2. So you're observing the attenuation when the, what is the attenuation when the wave is traveling from port 1 to port 2 under the condition that A2 is 0, that is port 2 is terminated. Now, this parameter actually specifies another thing also. We have already gone through that. It gives you the information regarding the transmission coefficient. It gives you the information regarding the transmission coefficient, which we had noted as T. So in the very starting sessions, we had discussed regarding these aspects. And if you remember, T is actually equal to 1 minus the reflection coefficient. So in we can define these also in slightly different forms. So these are the things what we can observe. So S11 and S21 gives you the reflection coefficient. This one gives you the attenuation information, and we also specify that it gives you the transmission coefficient information for the given microwave network. So this is what we have for the S-matrix representation for a two-port network. Now here when we observe, if I say there are n number of ports for the given microwave network, then I make the association in the same way. So in this case, the equation, what will be the equation? It will be, say if I take the first this thing, it will be S11 A1 plus S12 A2, A2 plus so on. If there are n networks, it will be S1n AN. So similarly, I continue up to BN. I continue up to BN. So here, if there are n number of ports over here, so I'll be having n number of reflected wave amplitudes associated with each of the ports, and I'll be having n number of the incident wave amplitudes. So if I consider any one port, say if I consider this port, I'll be having one incident wave amplitude associated over here and one reflected wave amplitude associated over here. If I consider, say, the nth port, I'll be having one incident wave amplitude and one reflected wave amplitude. So at each port, you have two parameters, that is the incident and the reflected wave amplitudes. So in this way, you have total of n, that is which is equal to the number of ports, total of n number of parameters associated with reflected wave amplitudes and n number of incident wave amplitudes. So this is the representation of the matrix, that is the S matrix representation for a n port network. So this is the general representation what we are having. So now what is the other observation we have to look out over here? So here, what is S11? S11, if I just consider it is B1 divided by A1, which is giving you what? It is giving you the reflection coefficient at what? At port 1. So in this case, so what happens is, since there are these many ports, right? There are these many ports. So when you want to identify what is S11, so in this case, the other ports have to be terminated. All the other n-1 ports have to be terminated, and then you obtain these parameters. So that is what you are looking out for. So here S22 is what? S22 is again associated with the reflection coefficient at port 2. So similarly, if I continue and I observe SNN, so which is at port n, it gives you the reflection coefficient parameter at port n. So this is what we can observe in this case. So here, what we have to look out is the diagonal matrix which is present in the diagonal elements which are present in the scattering matrix, right? They actually give the information pertaining to reflection coefficient. And the other parameters, what we had observed over here, they give you what? They give you the information pertaining to the transmission coefficient or the attenuation which is associated with that network. So this is another observation what we have to look out when we are representing when we are having the representation which is associated with the multiport network in S matrix form. So here one note what we have to look out is when we have to find the scattering matrix coefficients, that is S11, S12, those all things, right? We either terminated port 1 or port 2, and we need to terminate it with the matched load. So under such condition, what happens is either A1 becomes 0 or A2 becomes 0. So that is what we had specified over here. When A2 is 0, it is implied that we have match terminated port 2 with a matched load. And if A1 is equal to 0, it implies that port 1 is being terminated with a matched load. So that is what we had observed in the previous case. So this is associated with the representation, that is the S matrix representation of multiport network. Now, in association with this, right, we have a few other parameters which are termed as the losses which are present in the network. So what are those losses? That is what we have to look out for. So I'll come to these parameters. So I'll be discussing this. So this will discuss later. Okay. So here you can see that we have something we have specified PI, P0, A1, B2, S12, S21. So these are all discussed, and PR. So these are the three parameters what we have to identify first. What is PI, what is PR, and what is P0. So let us come to the block representation over here. So here you can observe what is PI. PI is the input power which is present at port 1. So that is if I'm powering the network and at port 1, I'm defining it with the value which is termed as PI. So this is the incident power or the power which is fed at port 1. This is the power which is fed at port 1. Now what is PR? PR is actually the reflected power at the same port. It is the reflected power at the same port. Now if I consider PI minus PR, this is actually the power which is provided or given to the device or the microwave network over here. So we have PI, which is associated with the power that is being fed or incident at the port 1, and PR is the reflected power at port 1, that is at the same port where PI is given. And this is the power which is actually being transmitted over the network. So these are the three parameters, that is PI, PR, PI minus PR. Now what is P naught? P naught is actually the output power at this port 2. So in this case, I am considering the two port network, and I am giving the analysis associated with the losses which are defined in terms of S parameters. So which we define it in association with the S parameters. So if I have to again just go ahead with that representation, since we have to represent it with the S parameters, right? We can just have a few discussions prior to that. That is, what is AN? It is the incident wave amplitude at port N. What is BN? It is the reflected wave amplitude at port N. So how we had represented in the previous case, right? The same way we had, that is, we had represented A1 and B1. So now this in general, we represent it as Vn plus divided by square root of Z naught, or in terms of currents, it is In plus into square root of Z naught. So what is this N representing? It is representing the port N over here. That is the Z naught at port N. So similarly, Bn is associated with the reflected parameters. It is Vn, that is the reflected parameter, Vn minus divided by square root of Z naught at port N, and it is equal to I minus into Z naught at port N. So it is associated with the reflected parameters. Now at the nth port, right, if I consider the representation over here, so what we have is we have the input power at the nth port is associated with this equation. We can represent it with the incident and the reflected wave amplitudes. So which is equal to half of magnitude of an square minus magnitude of bn square. So here n is associated with the port n. So this is input power at port n. So this is how it is represented, and this represents the power which is being dissipated at port n. So it is given by half of bn square, magnitude of bn square minus magnitude of an square. So when I take say bn common, so I'll be having the reflection coefficient representation over here. So that is what they have represented in this case. So slight correction in this. Actually, here it should be the dissipated power will be given by this equation. So this is the typo error which is present in the book. So please rectify it. So in terms of reflection coefficient at port n, it is given by half of magnitude of bn square minus magnitude of Rn its square. So where the reflection coefficient at port n is given by Bn divided by Rn. So this is what we have for the representations. So this is again the voltages which are represented at port n with the association with the incident and the reflected wave parameters, and the same if I make use of this equations, right, I'll be able to represent it in terms of AN and BN, that is the incident and the reflected wave amplitudes. So which is given by AN plus BN into square root of Z naught N. So Z naught at the nth port. Similarly, the current is associated at the nth port by this equation. So these are the equations what we have. So if we solve this equation for AN and BN, I can have the relation of the incident and the reflected wave amplitudes in terms of the voltage and the current parameters along with the characteristic impedance. So this is what I have for the representations. So now coming back to the losses which are represented in terms of S parameters. So first one is the insertion loss. It is given by 10 log pi by p naught. So where pi, so if I'm considering the two-port network, I'm considering the two-port network. So in that case, pi is the incident, that is the power which is fed into the port 1 or the input port, and p naught is the power which is available at the output port. So, and when I make association of pi with the A and B parameters, right? What we have is pi is given by magnitude of A1 square, since it is at port 1 and port 2 is the output what we are observing. So port 2 will be P naught will be given by B2 magnitude of B2 its square. So when we simplify this, what we have is we have this one represented by 1 divided by B2 by A1. So which is actually S21 parameter. So it is given by 20 log of magnitude 1 divided by magnitude of S21. So it is because of the property of S matrix, I can represent S21 as S12. So it is again dependent on the properties. In next coming sessions, we'll be discussing regarding these properties. So therefore, we have the insertion loss is given as 20 log 1 divided by magnitude of S21 or 1 divided by magnitude of S12. So similarly, we have the transmission loss or the attenuation. Transmission loss or the attenuation. So if I just consider what is the power which is being transmitted through the network. So if I just observe over here, Pi minus R is the power which is being transmitted and P naught is the output what you are observing. So what we have, so we have the transmission loss defined by 10 log Pi minus Pr divided by P naught. So again, if I represent these in terms of A and B parameters and try to simplify this, what I'll be having is I'll be having the representation which is given over here, which is 10 log of 1 minus magnitude of S11 square divided by magnitude of S12 square. Now, in association with the reflection loss. So here the power which is fed over here, it is Pi, and we have the power which is being transmitted is Pi minus Pr. So 10 log of this parameter gives me the reflection loss. So when I again simplify this in terms of A and B and then simplify it to have the representation for S, I have the in reflection loss which is given by 1 divided by 1 minus magnitude of S11 its square. Now what is the return loss? So it is 10 log of the power which is fed at the input and the power which is reflected at that port itself. So this gives me the overall return loss. And when I represent it in terms of the S matrix, it is 10 log of 1 divided by magnitude of S11. So this is what we have for representation of S matrix for a multi-port network. Then associated with that, we have the different losses what we have represented over here. All for today. Let us meet in the next session in which we'll discuss regarding the properties of S parameters or the scattering parameters. So let us meet in the next session. Thank you.
Thank you, sir.